So now that we've talked about the difference between a reversible and an irreversible process, now we can define what the Carnot heat engine is, or Carnot cycle. So basically we can still consider that we have our high temperature reservoir and our low temperature reservoir, and we have some cycle, and we have heat transferred in, heat transferred out, and we're getting some work net out. So the Carnot cycle, or the Carnot heat engine, still has all of the same components as a real, or as basically a real heat engine. So I'm just going to write that down. The Carnot heat engine still has all of the same components as a real heat engine. Basically, the Carnot heat engine still has a boiler, turbine, compressor, a pump. The difference is that the processes in the Carnot cycle take place in a pretty specific way. So what we want to consider is what makes the Carnot cycle unique. Like, what makes the Carnot cycle different from a regular heat engine cycle? Well, the main things that make it unique are that the Carnot cycle is ideal, which means that it's reversible. And basically what this means is that all of the components that make up the Carnot heat engine, so the boiler, turbine, condenser, pump, they're all done in a way that they're all reversible. What I'm going to do is draw a PV diagram representing the Carnot cycle, and then we're going to go through it step by step and look at how each process is working. So first of all, let's first draw our temperature isotherms. So this is one of our isotherms. This is another isotherm. So let's say that this is T high, and this is constant. Let's say this one is T low, and this is also constant. So let's say that we start here. So this is state 1, and we go to here. So this is state 2, and we're moving along this isotherm. So basically what we're doing is we're going from state 1 to state 2, and our volume is getting larger. So this is going to be, and since we're moving along the isotherm, this is going to be constant temperature. So this is isothermal expansion, and this is, since we're considering the Carnot cycle, this is going to be reversible. We'll expand on that in a minute. Let's draw the next steps. So next we're going to go to state 3, so that's here. And so we're moving along this path. And this is where our system is still expanding, and because the volume is still getting larger. So this is going to be adiabatic expansion. And then let's say that we move back to, so here's state 4. So we're going to move back along this low temperature isotherm. And so now we're compressing our system. So now this is called isothermal compression, and it's going to be reversible since we're considering the Carnot cycle, and I'm going to get to in a minute how that can be reversible. And then we're going to move from state 4 to state 1. So we're still compressing our system, and this is adiabatic compression. So what I want to do is look at each of these individual parts and take a closer look at what is actually going on. So what exactly is making the Carnot cycle unique? So let's look at this first step from 1 to 2. So from state 1 to state 2, we have reversible isothermal expansion. And this would, in a steam power plant or a Carnot heat engine. This would be taking place inside possibly a boiler, but we're just going to, for simplicity, we're just going to imagine a piston cylinder. So basically we have a piston cylinder, and so here's our piston and cylinder, and this gas is expanding, but it's doing it isothermally. And so there are a few things we need to consider. First of all, for this to be reversible, there has to be no friction. So there's no friction between the piston and cylinder, or between the mechanical components. But that's not the only thing that we need to consider for this to be reversible. The other thing that we need to consider is that, well, basically what we're doing here, so we're expanding the gas in this cylinder, and the gas is at the high temperature, and it's isothermal expansion, so we know that as gas expands, it's going to cool. So the only way that we can keep this gas at this temperature, or this T high, is if this cylinder is in contact with some reservoir that's also at T high. And so what's going to happen is, as the gas expands and it cools, some heat is going to be transferred from this high temperature reservoir to the gas, and it's going to maintain the gas at the temperature T high. Well, the only way that this heat transfer can be reversible is if the temperature difference, so if the temperature difference between the gas that's in the piston cylinder and between the gas that's in the reservoir is infinitesimally small. So basically we have to have the temperature difference has to be dT. So there's such a small temperature difference that it's changing by an infinitesimally small amount. And so the only way that this can happen is if the expansion process is happening in a quasi-static or quasi-equilibrium way. So basically this expansion is happening, this gas is expanding so slowly that the temperature change in the gas is this infinitesimally small amount, and so then when heat is transferred into the gas, it's basically a tiny amount. Basically what that means is we could reverse the process, so we could start compressing the gas and we could reverse it, and it would exactly follow the reverse process. So another way to look at this is, let's say that we have PV diagrams. So we're going from state 1 to state 2, and we're following this isotherm. So the only way that we actually know that this path is actually defined is if this process is happening infinitely slow manner. So this expansion is happening extremely slowly. Like one example of this is, let's say we have a pile of sand on the piston, and this is happening so slowly that we're removing one piece of sand at a time. So we remove a piece of sand, the gas expands by a tiny amount, the temperature decreases by a tiny amount, and a tiny amount of heat is added to the gas to maintain the temperature. And then we remove another grain of sand. The piston moves up by a tiny amount, and the temperature of the gas decreases by a tiny amount, and a tiny amount of heat is added to the gas to maintain the temperature. So this happens infinitely slowly. So the reason why this is reversible is because we could, say, put a grain of sand on here, so I just added a grain of sand. This is going to compress the gas by a tiny amount, which is going to increase the temperature by a tiny amount, and a tiny amount of heat is going to be transferred out of the gas into the reservoir to maintain the temperature. So basically the path that we follow to compress the gas is identical to the path that we follow in the reverse direction the path that we follow to expand the gas like this process path. Let's draw this in a different color. The process path that we're following when we expand the gas is going to be exactly the same as the process path that we take when we compress the gas. And so that's really what makes this reversible. And so if we say expanded the gas quickly, we don't actually know what the path is that this follows, so it could be like it could be something like, who knows what the path is if this happens, if the expansion happens really quickly. And so that means that when we compress the gas, we can't follow the exact same path back to the initial state. So the reason why this is reversible is because it's happening infinitely slowly, so infinitesimally small steps. And basically this means that it's quasi-static. So that makes this this process, like if we look at this, this Carnot cycle, the process from 1 to 2 for the isothermal expansion is reversible because it's happening, basically it's quasi-static, so it's happening extremely slowly, and it also doesn't have any friction. So now let's look at the next process. So the next process is from state 2 to state 3. So this is the adiabatic expansion. So let's go down here and write that down. So from state 2 to state 3, we have reversible adiabatic expansion. So basically what's going on with this is, let's draw our piston cylinder again. So in the first process from state 1 to state 2, we were expanding the gas with the reversible isothermal expansion. From state 2 to state 3, we're still expanding the gas, so this is going to be reversible. So this is adiabatic expansion. So remember, with adiabatic, there's no heat transfer. So basically, this is now insulated. So this is insulated. There's no heat transfer into or out of the system. As the gas expands, it's doing work on this piston. So it's pushing against this piston and it's doing work on the surroundings, and the temperature in the gas is going to drop. So the gas is still expanding. The temperature is going to drop from the high temperature to T low. So the temperature in the gas drops from T high to T low. And this is going to be a reversible, so this is going to be reversible work, and it's going to be reversible because we're going to say that the piston is frictionless, which means that there's no friction between the piston and the cylinder, and it's also in quasi-equilibrium, which means that the process is happening extremely slowly. So the process is both reversible and adiabatic. Now let's look at the next process. So the next process, we're going from state 3 to state 4. And so in this process, we're going to be compressing the gas, and it's going to be an isothermal reversible compression. So let's go write this down. So we're going from state 3 to state 4, and this is going to be a reversible isothermal compression. What's going on with this? Let's draw our piston cylinder again. So we have our piston cylinder, and this time we're going to be compressing the gas. As we compress the gas is going to heat up, and so in order for it to remain isothermal, because remember it's going to be isothermal, heat has to be transferred from the gas. So we're going to have, this is going to be in contact with a heat source. This is going to be T low. So this is going to be at the same temperature of the gas in the piston cylinder, but as we compress the gas is going to heat up, and so in order for it to maintain its temperature of T low, heat is going to be transferred out of the gas. And so this is going to be reversible in the same way that if we go back up to this step, so when we went from state 1 to state 2 with this reversible isothermal expansion, we're going to be doing the same thing with the compression, except we're going the opposite direction, but this process is still going to have to be infinitesimally small, so it's going to have to be quasi-static. So we can once again picture these pieces of sand on here, and since we're compressing the gas, what we're actually doing this time is we're adding one piece of sand at a time. So for this to be quasi-static, as we compress the gas, we're going to add one piece of sand. That's going to compress the gas by a tiny amount. The gas is going to heat up by a tiny amount, and a tiny amount of heat is going to be transferred out of the gas to maintain the temperature. If this happens very slowly, so we're going from state, let's go look at this. So we're going from state 3 to state 4, so we can draw that on here. So this is state 3 to state 4. If this process happens extremely slowly, what we can do is we can reverse the process, and it should follow the same path in both directions. So if the process happens quickly, we won't necessarily be able to reverse it and follow the same path back, and so then it would be irreversible. So this is going to be reversible because of a few things. First of all, because there's no friction between the piston and cylinder, and second, because it's happening extremely slowly. Now let's look at the last process. So the last process, we're going from state 4 to state 1, and we're still compressing the gas. This is going to be adiabatic compression. So we're going from state 4 to state 1. So this is going to complete the cycle, and this is going to be reversible adiabatic compression. So let's draw our piston cylinder again. So we're still compressing the gas. So we're at state 4, and to get back to state 1, we need to compress the gas even further. And we're going to do it adiabatically, so that means there's not going to be any heat transfer. So that means that this is going to be insulated. So it's like the process from state 2 to state 3. It was adiabatic, and so it was insulated. What's going to happen as we're compressing the gas is the temperature is going to increase from T low to T high. So basically we're increasing the temperature from T low to the original temperature of T high, and the gas is going to be compressed in a reversible manner, which means that it's happening extremely slowly. So this process is going to be quasi-static, and that basically just means that it's happening really slow. So let's just summarize this again. I'm going to summarize this on the PV diagram. Let's put our isotherms. I like to draw the isotherms first for this. So the isotherms are just constant temperature. So we have state 1, 2, 3, and 4. So we're going from state, and I'm going to number these, so 1, 2, 3, 4. So we go from state 1 to state 2, and this was the reversible isothermal compression. So reversible isothermal compression. And when we do that, we're going to have some heat transferred in. So that's going to be the Q high. And I'm going to also label these isotherms. So this is T high and this is T low. So then we're going to go from state 2 to state 3. And this is going to be reversible adiabatic expansion. And then we're going from state 3 to state 4. And this is going to be reversible isothermal. sorry, this one isn't compression. This process from 1 to 2, this is reversible isothermal expansion, because we're expanding the gas. So then down here we have reversible isothermal compression. And then from state 4 to state 1, I'm going to move that up a little bit. From state 4 to state 1, we're still compressing the gas, so this is going to be reversible adiabatic compression. And if we go back to this reversible isothermal compression, we're going to have some heat transferred out. So we're going to have Q low, so heat transferred out. And so really what makes the Carnot cycle unique is how the processes are done. So they're all reversible, so the processes are taking place in a really specific way to make them reversible. And basically our heat transfer doesn't cause a temperature change. So the heat transfer that doesn't affect a temperature change is an idealized process, because normally if you add heat you would expect the temperature to rise, or if you take heat out you would expect the temperature to decrease. So this is an idealized process when we're saying that we're adding or taking away heat and we're not changing the temperature. And we also have work that's being done with no heat exchange. So if I take a step back, this here, let me just do this. So these two processes, so the reversible isothermal expansion and the reversible isothermal compression, we have heat transfer that's not causing the temperature to change. So basically this makes this heat transfer a reversible process. And then we have, for the reversible adiabatic compression and the reversible adiabatic expansion, we have work that's being done with no heat exchange because it's adiabatic. And so that means that this is adiabatic reversible work. So the thing that's making the Carnot cycle is specifically how the processes are being done. They're all idealized processes that can't really happen, but where they're useful is they put a limit on what's theoretically possible, because if these are the best possible processes we can have, we know that we can't have a better process. So I'm just going to say that the Carnot cycle puts a limit on what's theoretically possible. So this is really useful because if we know what's theoretically possible, we know that we can't build something that say has a higher efficiency than what's theoretically possible. So this comes to the Carnot Principle. The Carnot Principle says that no heat engine or refrigeration cycle operating between two reservoirs can have a higher thermal efficiency or coefficient of performance than the Carnot cycle operating between the same two reservoirs. So let me just write that down. So no heat engine, and we haven't talked about refrigeration cycles yet, but we're going to talk about those. But no heat engine or refrigeration cycle that's operating between two reservoirs, so this would be reservoirs at the high temperature and the low temperature, can have a higher thermal efficiency, or for a refrigeration cycle, a coefficient of performance, than the Carnot cycle operating between the same two reservoirs. So basically this Carnot principle is putting a restriction on what's possible. So what we're going to do is we're going to calculate either the thermal efficiency or the coefficient of performance for our proposed process, and if it's higher than the Carnot efficiency, the Carnot thermal efficiency or the Carnot coefficient of performance, we know that it can't work because it's going to violate the second law. Two corollaries to this Carnot principle. I'll just put two corollaries. Our first one, so no heat engine can produce more work per unit of heat input than the Carnot cycle. Or, so if we write down the equation for the thermal efficiency, the work net out, so the thermal efficiency is equal to the net work out, so what we want, over what we have to put in. And we're putting in QH. And so basically the Carnot engine is going to produce more work per unit of heat input than any other heat engine. And then we can write a similar statement for the refrigeration cycle. So no refrigeration cycle requires less work input per unit heat, so per unit heat transfer, than a Carnot cycle. So what we want to do is we want to calculate the thermal efficiency for the Carnot cycle. And so, because if we know that a heat engine can't have a higher efficiency than the Carnot cycle, then we know that if our heat engine is, if we calculate an efficiency, say, less than the Carnot cycle, we know that our heat engine is possible, but if we calculate an efficiency that's higher than what the Carnot cycle says we can have for that particular cycle, then we know that what we're trying to do violates the second law and it's impossible. So we want to come up with a relation for the thermal efficiency for the Carnot cycle. Well, let's start with just the thermal efficiency. The thermal efficiency is 1 over QL, or 1 minus QL over QH. And then if we look at the definition, so this is from the definition of a thermodynamic temperature scale, QH over QL for a reversible process is equal to T high over T low. And so what we can do is we can plug the T high over T low into this equation for Q high over Q low. So then the thermal efficiency for a Carnot cycle, so I'm just going to put Carnot, is equal to 1 minus TL over TH. This is pretty convenient because basically we can calculate the Carnot efficiency by just knowing the temperatures of our two heat reservoirs. So we're going to use this relation. So use this relation to find the thermal efficiency for the Carnot cycle. And this will be with the temperatures. And these are absolute temperatures, so you're going to want to use Kelvin. So from this relation, since this is for the Carnot heat cycle, we also know that this is for a reversible cycle. So what we can do with this is we can say, okay, well, we know that the highest efficiency we can possibly have is basically the Carnot efficiency, so the reversible heat engine that's operating between the same T high and T low that we have. And so what we can do is, if we calculate the thermal efficiency, if our thermal efficiency is less than the reversible thermal efficiency, or the thermal efficiency for the Carnot cycle, we know that our cycle is irreversible. If our thermal efficiency is equal to the thermal efficiency of the Carnot cycle, or a reversible cycle, we know that our cycle is ideal or reversible. And if our thermal efficiency is greater than the reversible thermal efficiency, we know that this is impossible. So you can't have an efficiency higher than a reversible heat engine efficiency, or you can't have an efficiency higher than a Carnot heat engine. So basically, when you're trying to decide if your heat engine is possible or if it violates the second law, you're going to calculate the Carnot efficiency. So you're not going to be comparing your efficiency to 100%, because no heat engine can be 100%. The highest efficiency you can have in a heat engine is the Carnot efficiency, so you're going to be comparing your efficiency to the Carnot efficiency to see if your heat engine is possible or if it violates the second law. So let's look at one example. Let's say that we have a heat engine that operates with a 150 degrees Celsius heat source and a 20 degree Celsius heat sink. And we want to find the maximum possible thermal efficiency. Well, so what we have, we have our two sources. So this is T high and T low, and we have our heat engine, and we have some work out. So what we want to do, since we're looking for the maximum possible thermal efficiency, we want to calculate the efficiency for the Carnot cycle or for a reversible process. So if we go back to what we just derived for that, so the thermal efficiency for a reversible process or reversible cycle, which is the maximum efficiency we can have, this is equal to 1 minus TL over TH, which is equal to 1 minus, and then we need to convert these temperatures to Kelvin. So this is going to be 1 minus 20 plus 273 divided by 150 plus 273. So we're just converting those temperatures to Kelvin. And this works out to 0.307, which means that this is approximately 31% efficient. So the highest efficiency we can have with this particular cycle, with this temperature source and heat sink, the highest efficiency we can have is about 31%. So basically, if we try to design something that's going to have a higher efficiency, it's going to violate the second law, and it won't be possible. So basically, the process you're going to be using to determine if your particular cycle violates the second law is you're going to be calculating the thermal efficiency for a reversible or an ideal process, which is the Carnot cycle. And then you're going to be calculating your efficiency and comparing them to see where your thermal efficiency is. So you can determine if it's irreversible, reversible, or impossible. So in the next video, I'm going to be doing some example problems showing how this would work.